Okay, so this chapter that we're doing, we'll be relating force to how it causes rotation. So hence it's called turning effect of forces. And the formula, I think probably you might be familiar with, is turning effect of forces is equal to the force multiplied by its perpendicular distance from the pivot. Okay, let's just get on with it. And right, now let's take a look at example 1. So for example 1, we have a pivot and a plank placed on top of it. So we have a pivot. So I'm going to first look at the pivot, point out where the pivot is. And we have an 8 Newton force upwards to the left of the pivot. So we want to know what direction will this plank or this beam rotate because of the 8 Newton. So just imagine. So if you're not very sure, sometimes I always ask students to take a pen or pencil, and then you just try to imagine the scenario. Okay, so one hand pivot, and the other hand just, yeah. So you just visualize, so it's much easier if this is something new for you. Now, just to highlight, for rotation, there's only 2 directions. So there's no such thing as rotating up or down. So what kind of terms, or how do we describe rotation? In physics, we call it clockwise or anti-clockwise. So I just draw a quick clock face, okay, that will, so clockwise means this way, right? Okay, so now let's look at example 1 again. So we have labeled the pivot, and the 8 Newton force is upwards to the left of the pivot. So as you can imagine, the force will cause the plank to rotate in this direction. Okay, so in this direction, we will label it as clockwise. So the 8 Newton causes the beam, or the plank, so this is the plank, to rotate clockwise. So therefore, we call it a clockwise moment. So how do we calculate the moment? So clockwise moment due to the 8 Newton will be equals to the force, which is the force, multiplied by its perpendicular distance from the pivot. So as you can see, the 8 Newton is 0.6 meter from the pivot. And this will be your perpendicular distance. So the distance must be right angle to the force, so which is 0.6. So we get 4.8. So since the formula is force multiplied by distance, so the SI unit for turning effect of forces would be Newton meter. So of course, you always take note of what unit you're actually using rather than just blindly, So sometimes we can leave the answer in Newton cm depending on the question. All right, let's look at another example. So let's hop on to example 3 first. So example 3, similar diagram. We have a beam sitting on a pivot. So our pivot is still the same place. Well, the difference, if you notice, my 8 Newton is pointing downwards. The force is downwards to the left of the pivot. So just imagine, how will the beam actually rotate? So it will rotate this way. And this means that it is an anti-clockwise moment. So the 8 Newton produces an anti-clockwise moment. So it causes the beam to rotate anti-clockwise. Okay. So anti-clockwise moment, so I kind of sometimes use a very short symbol to represent anti-clockwise moment. So don't use it if your teacher don't allow it, okay? So anti-clockwise moment is equals to force times perpendicular distance. So I have my 8 Newton. And similarly, it will also be right angle. So the distance is right angle to 8 Newton between the force and the pivot. So we still have 0.6. So we have 4.8 Newton meter anti-clockwise. So even though the value is the same, both are 4.8, But if you were to apply a force like in example 1, it will produce a different effect as compared to example 3, right? Now let's look at the third case, which is example 2. Now, example 2, I didn't give more numerical value because I just want to compare. So what happens if your 8 Newton isn't even vertical in the first place? Okay, but not to worry. So just have an idea first. What kind of moment, what's the direction of the moment you will produce? So first, we have to always see where the pivot is. Same place. And just imagine if you were to push at this direction, this 8 Newton, and how would the beam be rotating? So it will also rotate somewhat like this. So therefore, it will also produce a clockwise moment. However, what's the effect if your 8 Newton isn't like exactly vertical? So to find out what's the perpendicular distance, as you can see from this diagram, your perpendicular distance is no longer 0.6 because this is no longer a right angle, right? So perpendicular distance is not 0.6 for sure. So what I would usually do is to extend, or rather like extend this direction of the force. So I will just add it in with dotted line. So imagine, so along this line, this is what we call line of action. So the action is along this line. So the force is along this line, okay? And after that, I would actually draw a line perpendicular to the force from the pivot to the force to the line of action here. Yep, okay, so you can see that this will be right angle. So therefore, the force, 8 Newton, is right angle to this distance. So this would be my perpendicular distance. So I can't use my 0.6 meters for the calculation of moment for 8 Newton in this case. Instead, I will have a different distance because that will be the perpendicular distance, as you can see. Now, I didn't have the value here, so I just want to illustrate this example. So basically, if you had the value and you wanted to calculate it, or able to get the value, so you will take 8 Newton multiplied by that particular perpendicular distance. And just to let you have an idea, this perpendicular distance definitely would be shorter than 0.6 meters because 0.6 meter is like a hypotenuse of a triangle, right? Well, you can pause the video and just take a second look. Right, so I hope this helps to understand how forces causes the beam to rotate. Thank you.